The rules of probability apply to the normal curve. For example, if we want to create two boundaries that collectively contain 5% of the scores in two ends of the normal curve, we could identify those boundaries using probability. The normal curve is a graph of all of the scores in a distribution. The most common, highest probability score is the mean. Notice the mean on the x-axis. The curve directly above it is the highest part of the curve. Now the curve represents relative frequency, so the highest part of the curve is also the part with the highest frequency. Scores closer to the mean have higher probabilities. Scores further from the mean have lower probabilities. Scores on the x-axis that are far from the mean have low frequency. There are very few of those scores. So how different does the test score need to be from the population mean for us to consider it unlikely to represent the population? We set an arbitrary cutoff value of 5%, i.e., if the test mean is so extreme that it would occur randomly less than 5 times out of 100, then it is too unlikely to represent the population mean. The value corresponding to a probability of 5%, or p equals 0.05, is z of a positive or negative 1.96 standard deviations. The probability of randomly choosing a score above or below positive or negative 1.96 is p equals 0.05. I will explain this in much more detail in a future chapter on z-scores. If you want to exclude p equals 0.05 of your scores, you can set a critical value to mark a region of rejection. The critical value is the 5% cutoff value that sets the inner fence of the region of rejection. The criterion that we use is 5%, p equals 0.05, although we could use other values if we wanted to. The critical value is also called the alpha level. Alpha, alpha value, alpha number, level of significance, significance criteria, significance value, cutoff score, or that number that we look up in the table. The region of rejection, aka the critical region, is the area under the normal curve containing scores that are so unlikely that we reject the idea that they represent our population. These are the small ends of the tails. In this case, they're colored in purple. Means in the region of rejection are so unrepresentative of the original population that it is a much better bet that they represent some other population. If the test mean does not lie beyond the critical value, then the sample is not in the region of rejection. Therefore, the sample test mean is likely to represent the original population.